I want to give a small introduction into Elasticsearch nowadays, combined with a more of a longish introduction into Spring Data Elasticsearch, just because many people are still using Java and the JVM. I think it makes a ton of sense to take a look at the integration with Elasticsearch, with the most common web framework, if you want, that being Spring and Spring Boot, especially nowadays. My name is Alex. I'm part of the Elastic community team. I used to be one of the Elasticsearch developers for, I think it was 6 years, before joining the community team last year. I was mainly responsible for alerting and the first implementation of the security plugin, things like that. So if you have any questions about Elasticsearch, hopefully I should be able to answer them. And if you have any further questions about alerting, and that was probably that I wrote a bug that you found. So let's get started. What's our plan for today? So this is my plan. That one is not tied to anything particular. We can move things around. You can ask questions. Probably I'm going to talk about it later than I'm mentioning it, but feel free to put anything into the chat. It's really just fine. And the first thing is rather an introduction of like, why do you need a search engine at all? What is Elasticsearch? And then we're going to take a look at Spring Data Elasticsearch. I do assume a couple of things here. First, I do assume that you're a Java developer. That said, it doesn't mean that you're unable to follow if you don't write any Java, but I think it's going to make it infinitely easier if you do. I will have a small demo in IntelliJ where we just show a few things. And then after that, I want to talk briefly about running Elasticsearch, right? Because it's not only, I dislike this whole notion of splitting development and operations. If you're a developer, you also have to know how your application behaves in production. And if Elasticsearch is part of your application, you have to know how Elasticsearch behaves in production and what kind of resources are needed, what do you need to look after. And of course, there's always next step. This can only be considered a small introduction from my perspective. And then I just want to talk about like, what things should you look into next? So why do you need a search engine or any data store in general? And of course, you need to store data. And usually the idea of storing data is that you're also retrieving it. And then retrieving your data needs to have certain properties, right? Sometimes it's about speed. You want to be able to really quickly answer questions. You don't want to run batch jobs in the background. You need to be sure that an answer is retrieved in a couple of milliseconds. Sometimes it's about scale. You want to make sure that you have copies of your data available. You want to make sure you can store an infinite amount of data, which of course is a lie. It's never really infinite. Also, it's bound to economic resources, so this won't really fully work out. And the other part is something that is, a concept that not every data store has, right? It's relevance. And we'll talk about that in a second. So the first thing is speed. I already talked about this. If you have a data store, most of the time, your data store needs to be available. Your data store also needs to be fast. This means that if you send a query, you want to make sure that the answer is there as soon as possible. I also talked about scale, and now I want to talk about relevance, because this is kind of a novel approach that mainly works with search engines. Think of a data store with a query language like SQL. Basically, you execute a query, a select statement, you define what columns you want to retrieve from a table, if you want to join table, whatever. But then you also have a lot of clauses that tend to reduce the result set, right? You have a where statement or a series of where statements where you filter for certain properties. And you could optionally also have sorting. However, the sorting only works based on values of all of your fields, but there's no notion of relevance in terms of, is this piece of document, this piece of hit, what I just found, is this really relevant to my query? This is kind of a concept that mainly exists in search engines, but does not exist in a lot of other data stores. And this is also something that is, kind of a thing you usually have to wrap your head around, right? If you search for something on Google and you go to the first result, you usually expect Google to give you the best result first. And the definition of what is best is really tricky, right? If most of us are developers and we are searching for something that is an ambivalent term, that means it exists maybe very differently in the real world compared to the IT developer world, then we usually expect the IT result to be scored up. But if our partner, for example, who might not be into the IT industry searching for some things, he may get completely different results because for your partner, those IT terms are not relevant at all. And this is where relevance also becomes interesting because it's very differently perceived depending on the user group you're in. This is also something that is insanely hard to implement for many, many users. Think of an e-commerce search, for example. But search or data stores are much more, right? This is just the kind of three things that we usually within Elasticsearch talk a lot about. But we also would like to have features like NRT, near real-time support. This means if you search data or if you index data, you would like to be immediately able to search for it again, and again, not wait a lot of time. Scalability becomes an issue for many, many data stores. You want to make sure that you have something called read scalability, where you may be able to sustain 1,000 queries per second. And by adding the same resources in your cluster again, you may want to be able to sustain 2,000 queries a second. So you would be able to scale your reads out. You also may want to have write scalability, where you don't only write data at one point within your data store, but you write it at two different locations to make sure that you can sustain an outage. Also, resiliency is important, right? Over the years, every ops person, system administrator, whatever, he's usually responsible for more and more systems, up to hundreds or thousands of systems with a single person. And why does it work? Because the systems got smarter, right? Something like Elasticsearch is able to figure out if a node is leaving the cluster or maybe has dropped without a purpose, like a network cut, for example. And in that case, the Elasticsearch cluster itself will figure out what are the next steps, how to make sure that all of your data is available. And this kind of resiliency is nowadays built into systems, and you don't have to do anything manually anymore. And also, there are other factors that are important if you want to run your data store, and it applies to Elasticsearch as well. Like you want to have operational simplicity. You want to be able to really pinpoint a problem and figure out what's wrong if there's, for example, a performance decrease. Also, the experience of your development team will or needs to be taken into account to decide what would be your best data store. The integration in your infrastructure, like how do you roll this out? Do you run this in Docker? Do you use Chef, Puppet, Ansible, EC2 instances? Do you use Elastic Cloud as a service? These kind of things are important. The experience of the whole team is important. And of course, like Elasticsearch or the stack serves a ton of different use cases, right? There's the observability use case with logs and traces and metrics, for example. There's workplace search if you would like to index your intranet data if you want. If you need to do security, there's dedicated agents nowadays that basically are able to report security incidents and allow you to monitor workstations and servers. I'm started with Elasticsearch from product search perspective. So the company I was in before I joined Elastic basically was running an e-commerce B2B marketplace for hotels and restaurants, for all the equipment, for anything you can see in a restaurant, for anything you can see in a hotel. That was basically a B2B platform, meaning that we were offering the platform and they were buyers and sellers. Think of it like Amazon for a special niche. And at some point, we needed to implement a product search engine. And this is where I had my first contact with Elasticsearch and started playing around with it and figured out that it's really nice to handle. And this was in German. So German is, from a search perspective, not a really nice language. So we had to deal with lots of corner cases, if you want. But that's a common use case as well, like a full text search. And Wikipedia is a very similar use case. Everything you search on Wikipedia, everything you search on Stack Overflow, everything you search on GitHub is basically an Elasticsearch query at the end of the day. And this is also a classic full text search use case with a fair share of twists. Like for Wikipedia, you want to make sure that the documents that get hit or visited a lot are scored higher, basically based on recency or based on views, for example. For Stack Overflow, it might be the voting of an issue, these kind of things. So scoring and relevancy is, again, very different for each of those. So in case you've never heard of Elasticsearch or the product overview in this case, I just want to briefly show you what part we are talking about today. You can see here there's the so-called stack. The stack are basically a couple of tools, Elasticsearch being the heart of it because it's the data store, it's a distributed system. Kibana is sort of the window into this. It used to be a dashboarding tool, but nowadays it's so much more. It's a management tool or management UI for many functions. And then beats and logs, those are basically ways to ingest data into Elasticsearch. And all of those, they kind of form three solutions. So those are basically three solutions for very concrete use cases like observability, security, and enterprise or workplace search, which I already talked about. And then there's always the question where to deploy all of this. And you can run this by yourself. You can run this on-premise by just downloading the archive or the packages. You can run this on Kubernetes if you want, with Elastic Cloud on Kubernetes. There's an operator. Or you can say, I don't want to run this at all. I just want to access the simple HTTP endpoint. Then you can also use Elastic Cloud, which is basically us running Elasticsearch and Kibana and parts of the stack for you. So today we basically only want to talk about Elasticsearch, mainly because this is where we will talk with using the JVM and Spring Data. There's no need to ingest any data because this is what we basically do from within our application. And most of the time, if you start with it, you will have Kibana and Elasticsearch up and running just because Kibana makes it really easy to talk to Elasticsearch. Yeah, this is just our how we make money slide if you want. There are basically different sort of licenses for different features. If you download Elasticsearch, it comes with 2 licenses, open source and basic. Everything including there is basically free to use for you. You don't have to pay anything unless you are a cloud provider and you would like to run Elasticsearch as a service yourself. And then there are features that are in the Go, Platinum, or Enterprise license. Plus you get support, what kind of features you do to basically make money. And of course, Elastic Cloud, if we run Elasticsearch for you, that also is a paid service. So if we want to talk about Elasticsearch in 10 seconds, from my perspective, it's a search engine serving different use cases like full-text search or analytics or business intelligence, however you name it, geo-based search, and you can also combine all of those three, and it's near real time. So basically the time between indexing and having the ability to search data is really low. It's distributed, so you can run it as one node on your notebook if you want to try to debug things. You can also run it as a cluster with several hundred nodes if you really need to. It's scalable, so it's basically scale up and scale out. If you give Elasticsearch faster hardware, it will make use of that. If you give Elasticsearch more nodes and it forms a cluster, it will also be able to utilize those. It's highly available and resilient. In this context, it means even if a node has an outage, that could be because of a broken network cable, that could be because of garbage collection, different things. Elasticsearch will figure this out by itself and take proper countermeasures to make sure that the cluster remains in a stable state. And the interface is HTTP and JSON. The decision for that is rather simple. HTTP and JSON are kind of the lingua franca of the internet for developers. Every developer knows HTTP as a protocol. Every developer knows JSON as an object notation. So despite working with the new technology, you don't have to have the additional overhead to work with an unknown interface if you want. And yeah, it's the heart of the Elastic Stack, as already mentioned. If you want to try things yourself, all you need to do is basically downloading Elasticsearch, unpacking it, and starting it. You don't need anything installed on your local system. Elasticsearch basically ships with its own JDK. That's why the download is rather big, but it also means everything comes packaged. Like you don't need to have anything else installed locally. And the same applies for Kibana as well. If you want to get up and running, Kibana also comes packaged with its own Node distribution. Kibana is written in JavaScript and TypeScript and runs on Node.js. So all of there is just everything with batteries included. All right. Let's dive into Spring Data and Spring Data Elasticsearch. So before I dive into Spring Data Elasticsearch, maybe just a quick introduction of what Spring Data is. Spring Data is basically a way to abstract away an underlying data store from your Java code if you want. So what you could do theoretically, I say theoretically because in practice I think it's going to be really hard anyway, that you have the ability to replace the underlying data store without really changing your application code. And Spring Data, used to be a project. I think it was called Hardest or something like that before it joined Spring. It's already quite old. I would say almost a decade. And was written by one person, which then joined Spring. And Spring Data allows you to have so-called extensions for all the different data stores. And one of those is Spring Data Elasticsearch. It's more of a community-maintained Spring Data extension. But also many of the core Spring developers help writing it and keeping it up to date. It also features a reactive extension, so Spring and Spring Boot also became more reactive, allowing you to kind of use reactive principles within your code to save resources. And if you do that, you can also use the Spring Data Elasticsearch reactive extension. One thing I would always advise is that you use the Spring Data Elasticsearch version, major version 4, which is based on Elasticsearch 7 something, and is also the default in Spring Boot 2.3. Spring Boot 2.2 and below features Spring Data Elasticsearch extension, which is based on Elasticsearch 6, which also means it's just missing a few more features, especially because there's a fair share of things that have been changed in the so-called REST client that is provided by Elasticsearch. And this REST client has seen a lot of new features and support in Elasticsearch 7, but not in Elasticsearch 6. So I always advise people, if possible, they should go with Spring Boot 2.3 and the Spring Data Elasticsearch 4 something. So let's quickly talk about the Elasticsearch REST client. That one allows you basically, well, every HTTP endpoint that is provided within Elasticsearch has an equivalent in the REST client. So the REST client is basically an ability to hide the fact that there's an HTTP API in the background talking to Elasticsearch. And one of the ideas is that this works with the Apache HTTP client, mainly because one of the requirements back then was that it should work on Java 8. Java 8 is end of life for some time, but still there's a lot of users of Java 8 who have not yet wanted to jump on newer Java versions. That potentially has a ton of reasons, like licenses, for example, or the faster release cadence, or that depending libraries don't work with new Java version. There's always millions of reasons. You could potentially not want to upgrade, even though you should, because the JVM development has become really rapid with lots of new features, bug fixes. So I would always strive to stay in the latest version. That said, the Apache HTTP client, I think, is one of the most common dependencies in many Java projects. So as the client depends on a certain version, you may want to consider shading to make sure that you have the right version in your dependency list. The REST client supports synchronous and cancelable asynchronous calls. So the Apache HTTP client has its own thread pool in the background that is used for that. The Elasticsearch REST client is thread safe, so you should always only need to instantiate a single instance, and that's about it. And you basically have two classes available. One is the REST client, which is kind of the low-level interface, and the other one is the high-level client, which features all the Pojo-based abstractions for the endpoint. Yeah, this is how it looks like. The REST high-level client uses this low-level or more low-level REST client, and that REST client uses the Apache HTTP client. This closable HTTP async client is basically from the Apache HTTP client project. So let's talk about a few basics of Spring Data Elasticsearch. If you've ever dealt with Spring Data in specific, you know that there are so-called template classes. Template classes allow you to basically execute CRUD operations. If you do this, or if you use this, always make sure you use the so-called Elasticsearch REST template, because that one uses HTTP, whereas the Elasticsearch template uses a so-called binary protocol that communicates with a different port with Elasticsearch. That one is in the future intended to be only for node-to-node communication, whereas using a client like Spring Data is supposed to be a client-to-cluster communication and not between nodes. So whenever you can, make sure that you really communicate via HTTP. Yeah, there's a converter for mappings. So if you have certain data types and you want to make sure you serialize them in a certain way, you can use this mapping Elasticsearch converter. And one of the big features of Spring Data is the repository classes. Repository classes basically allow you to extend or implement, depending on what kind of features you need, a certain interface. And this repository class then allows you to single document actions very easily without writing any code yourself. Because just on how you implement this interface and how you name your method, Spring figures out what to do automatically in the background. We're going to see an example for that in a second. And of course, there are features that are generic to Spring Data, like auditing, when you want to make sure that you always add information of who has changed an object, who has created an object. There are entity callbacks, so that you can execute code after a document has been saved successfully or before a document is loaded. But there are also concrete implementations of certain features of every data store. For example, for Elasticsearch, there's the ability to do efficient scroll searching, which means you can go through your whole data set, but as efficient as possible for this data store. Those are features that are really hard to abstract away because they're implemented differently in any data store. And so Spring Data has ways to just expose certain functionality for each of the data stores without abstracting or generalizing them away. So this is how a Pojo can look like. You can see here there's a fair share of annotations, but as a Java developer, none of us should be afraid of annotations anymore. I intentionally left out the getters and setters here, which you would need as well. But you can see here the first annotation here is the document annotation, and that one refers to an index. So for all of whenever you try to load a person class or a person object, the index used to query will be the person's index here. You can also configure a couple of features if you want, or a couple of settings, like if this index should be created when your Spring application starts, how many shards should be in there. So again, this is data store specific, but the main thing here is the mapping to a certain index name. Then you have the person class, the ID, sorry. The ID is really used as the unique identifier even within the index. So for the person's index, there can only be a single document with the ID 1, with the ID 2, with the ID 2000, you name it. Then there's the name field that doesn't have any annotation. Then you can see here that there's a fair share of annotations which are needed for validation, like the email annotation, the size one, the pattern one, the URL one. And then there's the field annotation. The field annotation, again, is Spring Data specific and even Spring Data Elasticsearch specific. You can see here that Spring Data infers the mapping out of the field annotation. So if you would create this index by your Spring application, Spring would look up, oh, what kind of type is it? This is field type keyword. all right, I'm going to set the mapping for this field to this exact type. You can also see that you can add some more information there, like in the created add field. You can set the date format. This is an ISO 68701 date, so kind of the standard date that you know from Elasticsearch, with the date, a T, and the time. And yeah, the other one is a field type keyword as well. You can also create lists. So lists are basically then arrays, if you want. They're stored as an array in the JSON, because what happens here from a Spring Data perspective is that everything gets converted into a JSON document at the end. And this will just become an array. And there are a couple of classes that are predefined how they should be serialized. For example, a point that will automatically become a geopoint type, so that you could do geo-point-based searches, like show me everything within 50 kilometers of where I am right now. And there's a question, which one is better, from Risa? Have a JSON for the fields you want to search, or use the annotations? That's a good question. If you're coming from a Spring background, everyone will probably tell you that you should go with the annotations. If you're coming from an Elasticsearch background, all of the projects where I use Spring Data Elasticsearch, I basically decided to have my own mapping JSON file where I configure this. That's also the reason why you can see here the create index set to false, because I have an application listener at startup that tries to create the index and store the mapping itself before anything else is done. That's kind of a personal preference, because me coming from a heavy Elasticsearch background, I will always pick the Elasticsearch option first. You can pretty much pick what you want, but my preference is pretty clear to have it kind of in one place and not scattered across a couple of annotations, because it's for me it's way easier to handle. Hope that answers your question. If not, feel free to drop a follow-up question in there. So the next thing that Spring Data is really well known for are the so-called repository classes. Repository classes basically allow you to do some CRUD actions if you want. And the Elasticsearch repository class here is part of Spring Data Elasticsearch. It features a couple of methods that are pre-defined, like, for example, find by ID. So you can call a repository find by ID, and then you will find the document with this ID, or certain searches. And the other interesting part of this is basically that you can have dynamic finders. This is one of the strengths of Spring Data Elasticsearch, that you can say, you can define a method called find by email, and the string you supply will be searched for in the email field, right? Or you could do find by email and first name, and then supply two arguments, the email and the first name. So this way, Spring Data basically infers the query it has to send from the finders. And this is a nice feature on the one hand, of course. On the other hand, you need to be careful if you rename a field, for example, because you need to remember to also change the finder, but hopefully this should be caught in your tests. Yeah, just here, if you're wondering what the types are standing for here, the user profile is basically what is returned by those finder methods. Sometimes it's a stream or a list or a single entity, and string is the type of the ID of the unique identifier. Sometimes it's just a number, like a long, if you have like an auto-incrementing field in a SQL-based data store, for example. One thing to pay attention to, and again, this is just what happens. This is not to blame Spring Data. This is just what naturally happens if you put an abstraction on top of a concrete implementation. You will end up with a certain inefficiency just because you want to make sure things work for everything the use case, and you don't need to configure your data store in any specific way. In the case of Elasticsearch, you can have a method named find by description ending with. And this basically means search in the description field and search for any content that ends with. And the query that gets created basically searches for star and then the parameter that you supplied. It could be any string here. And this is a really inefficient query from a search perspective. The reason for this is that you cannot go through this inverted index as you used to be. You can't go to one word and then see if it's there. You have to go through the whole inverted index. So basically you have to do something like a table scan if you come from a SQL store. Or if you think of an index in a book, you would need to go through each of the index and search for words that end with a certain suffix. And this is highly inefficient. And there are ways to change this within Elasticsearch. You could just store the field in a different way. For example, you could reverse each term and then also do a prefix search instead of a suffix search, and suddenly you're back to a more performant and efficient query. There's, for example, also a new wildcard type that has recently been added, which can help you with this. And those are things that, of course, cannot be known by Spring Data or Spring Data Elasticsearch because it's not aware of your mapping. You would need to implicitly enable these features. It's just something to be aware because sometimes this looks like a really nice solution and can be implemented very quickly. You just have to add another method to your repository and then you can search your data. But you need to know how your data store acts and what gets created out of this query. Because if you don't know, you will suddenly run into performance issues. So searching can be done on a couple of different ways. Of course, if you just search for certain features, like I was already talking about at the beginning, that you just want to filter on things, you could just use the repository class and write your own finders. But you can also use the native Elasticsearch way of things. And this is basically write your own query in Java. And this is from a piece of code that I wrote where you can see that we have a filter. So this is a Boolean query with 3 filter clauses. So this is really just to decide if a document is in or outside of a result set. Same for the must not part, but there's also a must part that is kind of adding some sort of randomization based on the timestamp if you want. And this is something that you can't write with a repository finder. So you basically have to fall back to the native way of querying here, which again, for me is rather natural. So I prefer this because as an Elasticsearch developer, I can immediately see what is happening here and I don't have to understand the framework in the background. But again, that is a matter of preference if you want. And here you can see that I'm just want to retrieve a single document if you want, and that's about it. And as you can see here, I'm using the REST template and I'm calling search1 to make sure only a single document is returned. You can also just count things if you want. So again, the Elasticsearch REST template offers this functionality with a count method where it can have different kinds of queries. One is the native search query, and you can also use the so-called criteria builder within Spring Data, which again abstracts away the underlying data store. So you don't need to write Elasticsearch specific query code here. This criteria builder is also used in the repository class when the finders are created dynamically. So that's kind of using the same technology. And yeah, this is just basically counting the number of hits that are being returned. This is another way of writing queries. You can see here that there's a query annotation. And the query annotation contains the query and the parameters. You can see here the $0 and here's a $1, which refers to the first and the second parameter. And because there's a count in the method name in the repository itself, we are basically running a very similar count in here. Again, I'm not a super big fan of this, mainly because you're putting JSON in an annotation, and I don't think this is super readable from my perspective. But if it solves a use case and you only need to use it once, then by all means, like don't work around the framework that you basically got, right? I would probably have written this again with a native query builder to make it more readable. This also means you have to write valid JSON within this annotation to make sure everything works as expected. which if we add another query clause, maybe slowly but surely becoming complex and hard to read. You can also use aggregations, again, mainly because we are just using the underlying Elasticsearch query capabilities here. So what happens here is that I'm using a term segregation to split my dataset based on the email of a user. And then I'm running a sum aggregation here to calculate a kind of score across all the documents that are returned here. And then you can also add another sub-aggregation. So this looks remarkably the same than basically any kind of aggregation code you would be writing in Java just using the Elasticsearch REST client. That's again mainly because there's no real notion in Spring Data Elasticsearch to use aggregations, because you're usually dealing with things on a single document level in that case. And that is fine. So that's that. If you have questions, drop them in the chat. I think I need to figure out how to get IntelliJ on the right desktop. You should probably see it right now. I know this is rather small. Let's do the demo mode. That one, awesome. So let's start with the entities. The entities is something you already saw. So this is a sample application that is also in GitHub. I can just drop the link in the chat if you want. Sorry, over here. It's this kind of application. And what it basically does, we can just take a look at where it's hosted. It's basically a small application. Again, I should probably increase the font size to make this more readable. So you can basically index links here, and then this executes a query and has a special scoring formula. So it basically takes the age into account so that newer links are considered more important, but it also takes the votes into account. So in this example, this is the highest voted article, and despite its age, it's pretty much scored, or it's scored quite high. And here you can see that the article, which is newer and has more votes, is ranked higher than the one with less votes that is older. For example, here you can see that the number of votes is more important than the age. And this is the kind of relevance I was talking about earlier, that I basically came up with some sort of special query to decide what is more or less relevant. And yeah, you can just clone the application and run this yourself. This is a Spring Data application. You can log in. You need a GitHub authentication token, so you can log in. And because I'm an administrator here, I could delete links, but I could also upvote them. Now it has 210 votes. And you can see here, I can only upvote them once, not twice. You could get a shareable link here. So this is just a single link view with a shareable link. You can, of course, also execute a search like for ingest, and you will see all the results that contain ingest, again, with this kind of custom scoring formula. So that's the core application. And it basically consists of two entities. One is a link, right? This link is something that you just saw, like and has a few fields. So there's an approval process. If you just put a link into that application, it's not shown yet. You need an administrator to actually approve it. And there's a user. So the user contains a list of fields where the user already has voted on the different links. So you can only vote once. This is how to keep track. And it contains the user ID, which basically is your GitHub login. So if we go back to the app, you would see here, for me, it's SpinScale. That's my GitHub login. All right, so the link itself doesn't have a ton of features. It's mainly consisting of the URL, the title, and a description and a category. The category here is used for the icon. So if we search across everything, you can see here that's the Elasticsearch category, that's a cloud category, and this is something that can be specified when you submit a new link that we could do here now. So what else do we need? Basically, we have two controllers. We have a user controller that basically contains the main site. So this is the page after login. There will be this one. There's also the ability to check for non-approved links. That's a pure administrator function. So I basically have a couple of methods here to make sure that this user is an admin. The way this works is that the admin service can be set by a system or by an environment variable. And I could just put the admins that should be able to change data as an environment variable before starting up the application. So in order to be an admin for myself, I just need to set my GitHub user in the admins variable, like spin scale, and that would be it. Apart from that, this one would just search for unapproved. You can see here that I'm basically running a query and put the number of results in the links attribute. The other part is the link controller. That one deals with concrete links, like showing the ID of a link, having the ability to submit a new link, the form you saw a couple of seconds ago, having the ability to vote for something. That's also something you saw. And being able to approve or delete something if you are an administrator. You can see here, there's the ensure admin method. Again, this could be solved in different ways using Spring Security. I just opted for the one that is, from my perspective, the most easy to read, but that's about it. So what else do you need as a configuration? This is basically coming back to the question earlier in the chat, which one is better, have JSON for the fields, or use the annotation. And this is basically where I opted to have JSON for the fields. If I would do this again, I would probably not put JSON in here, but have a file that I'm loading on the beginning. That's basically what I did in my other application that is live right now. And then you have this on application event in the application listener with the application ready event. And this means the moment the Spring application is loaded, I'm trying to configure and set these templates. I'm also doing a rollover. So I have index lifecycle management enabled for this feature. So I basically have a new index every couple of gigabytes, like every 10 here, every 10. So if someone would add a lot of data to this application, it would figure out to roll over indices automatically without me doing anything. There's the ability to index some sample documents. So if you run this locally for the first time, if you clone this project and run it locally, you will end up with a couple of sample documents. One of the things you have to do is just spin up a local Elasticsearch instance. This is the sample data, so that's about it. There's a web security config class, which makes sure that we can log in via GitHub. Again, there's nothing special here. I also have a little bit of special code to read the Elasticsearch configuration from a single environment variable. You may ask yourself why I read so much from environment variables. That's kind of a habit, because often when you deploy apps in Kubernetes or somewhere else, and this data needs to be retrieved, like the sensitive data needs to be retrieved from something like Vault, it usually gets exposed in environment variables. And that's why everything I configure here, I usually also put in environment variables. Also, they're really nice tools for local development, where it's really easy to just have your local setup in an .env file and load it when you change into a directory. This is, I'm doing some APM, or I'm using APM within this project as well. I can show this later on as well for the application that is up and running on my domain that you can also access, like this one. It's over here. We can take a look at the APM data later. So yeah, that's pretty much about it. There are a couple of tests. I mean, I have a few unit tests to make sure that I cannot store that HTML gets stripped if you send HTML in the form. And there's a few test classes. This is really just like the lowest test classes I could get. I'm not using the MVC test annotation that the way you should usually test your Spring applications, because it creates an application context and also reuses that one across classes. That would be the best step to actually do here. The test classes in here are just using a lot of mocking. Yeah, I think I showed every class over here, so there's not much. In case you're wondering how I rolled out everything of this on linkrating.spinscale.de, I use this service called Covery. You can think of it as a kind of Heroku if you want, but for me it looks easier to handle. It's quite a new startup from Paris, and I like a lot the way where they're going, making it really simple to deploy applications, because like this one doesn't require you to configure any YAML. It's really just pushing to your branch, and everything else gets done on the Covery side. Because I really don't want to edit any YAML just for pushing out an application. All right, so that was a quick demo. If you have questions, put them in the chat. We can go through the code later on if you want. You can clone the code and run this locally. And now the last couple of slides is more about running Elasticsearch, because now we only saw everything from the application developer perspective. And I mean, that always looks easy, right? You fire off a few queries, you get back your data, you store a little bit of your data, and everything is fine. Of course, like the reality is always different, especially if your app is really popular and you write and read a lot of data. Then thinking of creating strategies and scaling your cluster suddenly makes a lot of sense. One of the things I always tell people is that you should not overshard your data. It's just something that many people tend to do. Let's say I want to create an index with 50 shards or anything like that, and each shard then just contains 500 kilobytes of data. You should always start with a single shard and see how you scale, because a single shard can easily contain 20 to 50 gigabytes, depending on the use case. Another important thing is the file system cache. That's something you probably know from every operating system has it, but it might be that you know it better from systems like Linux or OS X. If you go to your terminal and you type cat file, and you do this for the first time, it usually takes a second to show you the file contents. If you do it immediately after that, the file contents are shown immediately. The reason for this is that the operating system thought if it has free main memory, that it puts this file into the free main memory, because there is a likelihood that you're going to read this file again. And this is a mechanism that Elasticsearch and Lucene, the underlying full-text library Elasticsearch users, make heavy use of. This is also the reason why we always tell our users never ever use more than half of your system memory as the Java heap. So the rest of the system memory will be used by the file system cache. It's not lost. That's a really important feature. Then another thing I always tell people is that you need to performance test before going live, and you need to do this on your data with your data access patterns. There's a tool called Relevancy. It's a macro benchmarking tool. You can see here, it's seeing quite some development, or even 1.8K commits. It's maintained by a team within the Elasticsearch team, by a sub-team. And it allows you to really test Elasticsearch against your data to easily find regressions, things like that. Sometimes maybe just a change of your mapping might cause a regression because a certain query suddenly gets really slow. And also capacity planning is important. There's a dedicated webinar for it. And we basically used Rally ourselves. We have nightly Elasticsearch benchmarks, which you can also visit under benchmarkselastic.co. We can just take a look at this one live. So we have different data sets here that we test every night, like HTTP logs, because it's a common use case. and the New York City taxis data set. This is the geonames data set. So there's a couple of different things. Let's take a look at the last 6 months, because I expect some changes there that I just need to watch. And this is the memory. You can see here that there's always a ton of small spikes. The reason for this is that no benchmark really is all the time the same. You always have some amount of jitter in there, depending on your environment, on your setup. All of this is running on bare metal machines, but still there's a certain kind of jitter. So in order to get good results, it makes a ton of sense to run those benchmarks in a nightly fashion. For example, you can see here a certain switch that changed the memory consumption. Right, you can see here that the percentile of certain queries suddenly increased, and this makes it easy for us to spot this and make sure we fix this before we basically issue another release. And this is something you should do with your own data as well. All right, what kind of resources does Elasticsearch need? You need some storage, like just to store data. Of course, the faster your storage is, the faster the retrieval is. So if you have a lot of hot data, like data that gets frequently accessed, that gets frequently written, it just makes a ton of sense to put this on SSDs. If you really want to store a lot of data, maybe HDDs are economically more feasible. Yeah, memory gets used for the JVM heap and the OS cache. There are some other small contributors, like native memory to read from the sockets, for example, that is used by Netty, the networking library within Elasticsearch. But this is the kind of biggest consumers, if you want. So the more memory you have, the more memory you can give to the OS cache, which makes it usually rather fast. On the other hand, if you have really fast SSDs, maybe you don't need so much memory. Again, it's often playing a game of economic feasibility, if you want. Regarding compute, if you add more CPUs to your system, especially if it's just a virtual system, we basically scale the thread pools within Elasticsearch based on the number of available CPUs. So this allows us to do more things in parallel. This would allow you to index more data in parallel. This would allow you to sustain more searches in parallel. So adding CPUs will allow you to do more things in parallel if you want. And of course, lastly, the network. The formula there is pretty simple. The faster, the better. If there are outages and you have to move a 50 gigabyte shard around, you can have a lot of advantages by having faster networking there. And of course, if you don't own the network, which most of us nowadays do not, you just have to be careful with cloud providers and what kind of performance they promise, because sometimes this performance is just a burst rate that can be sustained over a short amount of time, but it's not constant. And this means you need to figure out what your constant network speed is to make sure how long copying data would take. So before we open up the discussion, one thing I can always tell people is, as nice as this abstraction layer of Spring Data pretty much is, you should not forget that you sometimes can improve your search, and that could be the relevance or your search performance, by writing the right queries that may be really different from what something like Spring Data Elasticsearch offers, by changing the mappings and use a certain type. So this means that start with something like Spring Data Elasticsearch, because it probably offers you an abstraction of a mechanism that you already know if you've dealt with Spring Data before, but question how the searches are actually working. Especially what would help a lot here is to monitor your queries and your query speed and these kind of things, just to make sure that you see when something is really off and really slow. Same is about your model. So what you basically define in Java. There's also something that will not stay static. And that's something you need to be aware of. This means you need to have a proper mechanism in place to maybe change your mapping in your existing index, or you need to have a proper mechanism that if you do backwards incompatible changes, like changing a field type from an integer to a string or vice versa, that you have a mechanism to properly reindex your data, and that you also have a mechanism that your application can deal with both cases for a certain amount of time before you change this again. This is really important and needs to be kept in mind when you write your application, right? Upgrades, changes of your mapping is something that you always have to cater for. Yeah, and of course, performance. Maybe you're lucky and performance is not so important. That might be as well. Then don't spend a lot of time on performance. But if you're trying to deal with SLAs and your customers keep telling you like you should not break an SLA of 50 milliseconds, whatever, then you need to figure out what your expected throughput is. And throughput is not only the latency of a search, it's also the amount of parallel queries that you can sustain. And are they limited by your Spring application? Would you need to scale your Spring application first, or are they limited by Elasticsearch or by another data store? This is something that you are responsible for as a developer and need to figure out. It also means you need to make sure that you have proper logging in place, that you can extract these kind of statistics. And yeah, this is my favorite pro tip of running in production. This was one of the first things I did at my previous employer. I never wrote to concrete indices. I always wrote to aliases. And this allowed for so much more flexibility. Imagine that you have a full data set in one index and you suddenly figure out this index needs a shard more. Then you can trigger a reindex in another index in the background and at some point just point your aliases back and forth if you need to. So this gives you a lot of power. And for me, from a developer perspective, an alias is an interface. An alias is a contract, right? You query something like persons, and you really do not care if the persons index is an index with a single shard, is an index with 10 shards, or is maybe hidden between 10 different indices with 10 shards, like persons 1 till persons 10. And you can hide this away with aliases. So for me, an alias is an interface which hides the concrete implementation, but from an outside perspective, as an application querying Elasticsearch, I always get the same endpoint, and this is super important. You should probably also have different aliases for reading and writing. At my previous company, unfortunately, a full export of our data took like 2 hours because it needed to be joined across 25 tables to get the data that we needed for Elasticsearch. And this way we had one alias for reading, and then we could trigger a full export and had another alias for writing to write into a new index and then flip those switches as we would like to. And that was really important for us as well. Yeah, one more thing. Again, this highly depends on your use case. If you have more of a CRUD use case, you probably don't need so much search functionality. Like relevancy is probably secondary because you always query by ID, or you're just getting back a couple of results and you don't really care in the order. There's a reference documentation for Elasticsearch, which from my perspective is really good. The same applies to Spring Data, and especially Spring Data Elasticsearch. It's quite a lot of documentation, but it's really well written and it helped me to figure out things. So before starting like one app 4 months ago that I wrote for my team using Spring and Spring Data Elasticsearch, I never did a Spring application. I've been doing Java for over a decade, but a lot of that was Elasticsearch, so there was no web development. And before that, I used different web platforms. And the reference documentation helped me a lot to really get up and running with Spring and all the Spring mechanisms and also Spring Data. So yeah, and if you do a search application, like this is also something I learned the hard way from my previous employer. Like you can spend a lot of time implementing nifty and neat features or coming up with your own fancy relevance algorithm because you think it outscores everything else. But you should always ask your users about expectations and just go to one of your customers, one of your users, like show them, just give them a notebook and tell them like, look, this is what you should do. How do you approach this? And we spent a lot of time implementing a search as you type functionality like 10 years ago. And it was really good. And we were really proud of as developers. But then when we went to the first user and just like put the notebook in front of him and tell him like, look, we're searching for this specific product. What do you do? He just typed the product and he didn't look up to the screen. So all the fancy suggestions that we showed, like they were never used. And this is just something to keep in mind if you write these kind of applications, that it's really unexpected sometimes what a user is actually doing compared to what you expect him to do. And like, don't try to outsmart your users. It's inevitably going wrong most of the time. Yeah, one more thing, if you test, you should totally go with test containers. I hope you know this. Test containers is a testing library that basically allows you to start Docker containers within your unit test or integration test, hopefully. And it also features a Elasticsearch container. And this means you can pretty much fire up an Elasticsearch instance within your tests as long as you have Docker up and running. And this way, it makes it really easy to also fully test your application. If you fire up a Spring application context on this your Spring application, in combination with test containers, you can do really neat end-to-end tests. Also to figure out things like if your upgrade procedure is working, stuff like that. So test containers from my side is highly encouraged the moment you have to deal with Elasticsearch and Spring, just to come up with complete end-to-end tests if you want. So yeah, these are the resources. I showed most of that with the exception of the Spring Data documentation, but yeah, that's not a big thing. It's this kind of documentation. I really like it, lots of code samples. And if you've dealt with Elasticsearch or Spring before, I think it helps a lot to get started. Most of the other things are already left there. I will share this, the slides later, so you can take a look if you want. Yeah, that's it. We should have some time for Q&A now. If you want to test Elasticsearch as a service, go to cloud.elastic.co. You can basically fire up a cluster and test it for 2 weeks. There's the subscriptions if you're interested in more. I think one of the most important things here is our discussion forum. So if you have any question, just go to discuss.elastic.co, and you can basically see here the ability to ask any question. You can go here to the different solutions. So the Elastic Stack would, for example, be the one for Elasticsearch over here, and then ask a question here. The only thing I always ask people before writing a question is making sure that they give the ability to reproduce a problem. That just makes it so much easier for everyone reading your post that they can maybe just reproduce a problem because you supplied the mapping, the index, and whatever you're querying within a small snippet to understand what is wrong, and also to understand what you intended to do and what is not working as expected. They will just save a ton of time. Yeah, you probably know community.elastic.co, otherwise you would not have found this meetup. It's kind of our community site where we aggregate all the meetups. As you can see here, the most important one for now is definitely the, where is it? The virtual part. We basically have 3 different virtual geolocations just because of time zones, even though many of those overlap, so you might want to take a look. There's the EMEA virtual for the Europe region. That probably is the one which is best in your time zone. And most of our talks, basically everything you can see on community.elastic.co also gets recorded. This is the link. I can just paste it. We basically have a dedicated YouTube channel for that one that you can follow. We just created last week, so it doesn't feature a lot of subscribers or anything like that, but we basically upload every single talk there. So if you want to know more, just go ahead and enjoy the show over there. There's tons of videos that you can watch. As we can see over here, like the list is already, I think it's almost 70 videos right now, and we keep adding a couple of them per week. All right, that's that. I think we have some time for Q&A now. I can also show APM if you're interested. I just need to stop screen sharing for a second to log into the cluster and go from there. But if you have questions, now would be the perfect time to ask them.
Thanks, Alex, for the presentation. Si vous avez des questions, n'hésitez pas. Si quelqu'un veut intervenir directement, peut activer son micro et poser toutes vos questions directement à Alex. Or if you can, Alex, show some few words about APM.
Yes, totally. I'm still trying to find the right credentials, but I think I'm there in a minute. Give me one more second.
Okay.
So what every one of you could do is to help create some more data while we have this wonderful webinar, is to just, if you open this link one more time, you may also just click on the login button at the top, or just click a link, anything like that, which creates some data, it creates some traffic, and that should fill up the transactions. So let me try to reshare my screen, and then we're gonna have a quick talk about APM. So I'm on the Kibana. You should see my Kibana screen, right?
Yes.
Yes, okay. So if we go back to the screen after logging in, this is pretty much what you see. This is basically the cluster that also consists the underlying data of my application. So we can take a look at that one as well, and then go to APM. Let me again do this a little bit bigger. I hope that's halfway readable. So if we take a look at the indices, we have a couple of APM indices. And those APM indices are basically where the different data and configuration is stored in, if you want. And we also have this links index. That's basically the data that is used in the Spring app. You can see here, there's an underscore class field that gets automatically added by Spring Data. And it basically reflects the class that this entity is supposed to be serialized into. That gets more useful when you have different subclasses, for example, that get stored in the same index. You have the category, the title, the description, the URL, who submitted it, the created at timestamp. More recent Spring Data versions allow you to write a string-based date here, which makes it much more readable. But I think that's only in the 2.32, unless I'm mistaken. That's still rather new. And then there's a votes field, and this votes field is used for the query. So if you take a look at the mapping, get links mapping, the votes field has a subfield called from type rank feature, and rank feature allows you to do this feature that based on the value within the field, a document is considered more or less important. So if two documents have the same number of votes or have the same fields everywhere else, but not on the number of votes based on the query I execute, we basically get the document with more votes ranked up higher. So if we now go to the APM section of Kibana, what basically happens here is that I have configured this Spring app, and if we go to IntelliJ, to the creating application, you can see here that I'm basically attaching the so-called Elastic APM agent before the application gets started. You could also do this using a so-called Java agent from the outside. But because I'm just doing everything in my app and package this within a Docker container, this for me was the most convenient way, but this again depends on how you deploy your own applications. What basically happens here is that when this piece of code is called, the agent instruments the whole Spring application. And this means it starts measuring runtime of certain calls. And it also sends this data to the APM server. So there's another additional component that is an APM server. If we go to Elastic Cloud, which I am right now. So this is the cluster that is basically running for this. You can see here that there's a dedicated APM server that you basically can configure as part of Elastic Cloud. It doesn't cost anything extra. It's just another process that runs, that retrieves all of the APM data from the agent. And what happens here is that we can now take a look at the APM data within the APM app. We should probably reduce this to the last 15 minutes. And you have here a couple of graphics that allow you to see how much time is spent in which part of the application. So you can see here that there's 0.7% of your time spent in Thymeleaf. Thymeleaf is the rendering engine of Spring, or of this Spring application that's used to render out the HTML. Given that it's just 5%, it's probably not worth optimizing. Whereas in other parts of the application, it's 80.8% Elasticsearch. So it suddenly means that your Elasticsearch queries take a lot of time and may probably worth taking another look. However, as you can see here, the average duration of all of our requests is really, really low with 32 milliseconds. Also in the 95th percentile with 152. Looks rather okay if you want. Like user controller main, if we go back to the code, we can just open the user controller and jump to the main method. And you see that this is the piece of code that basically got instrumented, which runs in 152 milliseconds. It executes a new Elasticsearch query on every request. You can see here the bool query buildup. So I would say it's probably fast enough most of the time. You can see here there's an increased request with 66 per minute. There were a few people clicking around. That was probably me hitting reload a couple of times. You can see here the distribution of this, like how fast, how slow this was. And you can see here in what sub transactions or in what sub pieces the single request was split in two. So in this example, the whole request took 21 milliseconds, and 17 milliseconds of that actually were a query, and 1.7 milliseconds of that was the Thymeleaf rendering. So all in all, this was a really fast request. I would not be too worried about that. Maybe we find some slower request, but most of them are in the same energy. And what happens here is basically that the Java agent automatically instruments every Elasticsearch query because it instruments the Apache HTTP client. It instruments part of Spring. In this example, it's the Thymeleaf rendering. And this here, the whole user controller main thing, it's called a transaction. And every subpart of it is called a so-called span, which is basically a part of a transaction. You may have heard that from other tools as well, because the terminology tends to be the same nowadays. But this is basically the way how you can see the different speeds of execution. And if you would like to optimize something here, you will probably take a look at the Elasticsearch request because it takes the most amount of time when a single request is being executed. Yeah, you can see here there's also an impact graph that should just help you a little bit to see where to take a look. And this impact graph is based on the total duration, but it's also based on the number of requests. If you only have one request that takes 10 seconds, but you have 10,000 other requests per second, then this one request, which maybe on its own endpoint is not considered so important and doesn't have such a high impact because your runtime gets lost somewhere else. This is just something to basically keep in mind. So yeah, you can see here, there's not a lot of requests right now. That's a rather dead app. If I would create or set up a workload generator in the background, that might have been helped. But this is the basic idea. There's also a couple of more features here. If there's an error or an exception that can be logged explicitly, and you would see here an overview over your errors. There's also an overview over your JVM. So how much memory is needed, how much threads are being used, and you can take a closer look at this one. You would need to configure the host explicitly if you would like to see it here, but you can see here that the CPU usage is rather low, the system usage is rather low. This is really a small app, so there's no need to be worried. You can see here the maximum limit of this is 0.5 GB. The average use memory is 83.5. So the garbage collector keeps this low. You can see here some more resources being used and then the garbage collector kicking in. Same for the non-heap memory. You can also see here that some garbage collecting has happened. The copy part, depending on the garbage collector, this can happen in parallel and doesn't stop the world. The thread count is rather constant. If you would hammer the Spring application with more requests in parallel, the thread count would probably go up because I think it uses Jetty by default in the background. Oh no, it's Tomcat, sorry. And some more garbage collection. These are all things you pretty much get for free. And there's also a feature called the service map, which is better in this version. I'm still using an old version of Elasticsearch for this cluster, which again would not help us a lot because we only have a single service, but the service map is super, super useful the moment you have several services talking to each other, because you can basically follow the steps that each service is going through your stack. Yeah, you can also add some sort of alerting here so that you want to get alerted when there's a certain threshold being crossed, like the memory, for example, or the transaction duration, these kind of things. So if you know all my requests take 100 milliseconds max, you may want to get notified when suddenly all of your requests take 200 or 300 milliseconds, which may be because maybe your container is overloaded or things like that. Then this is definitely something you would like to know about. Also, this is kind of integrated with other tools. So if you run this on Kubernetes, you could jump to the infrastructure UI now and take a look at your Kubernetes pod if you wanted. As this is running on an external platform, I don't have any further information about the underlying container technology from a monitoring perspective. Yeah, so that was the APM intro. I think if you want to play with this, around with this locally, keep in mind that you need another dedicated service. That's the APM server that runs on port 8200 by default. It just needs to be there to retrieve the data and send it over to Elasticsearch. It's doing a little bit more. It can not only batch up the data, but it also has support for service maps. If you also use APM on the browser side of things for RUM, real user monitoring, so that you can see how long does it really take from the moment a user has clicked the button until the whole data has gotten back to the user. So it also takes the latency of the network into account, which we just can't see with this way of things. So if you want to use APM on a full scale, if you want, you also may want to make sure that you kind of monitor from start to end and not just something in between like I just showed you here, right? I know that the time leaf rendering is really fast, but I have no idea how long my SSL or TLS handshakes are actually taking. If there's a load balancer in between, it takes a lot of time. And this is something you probably would like to have monitored as well at this stage. All right, I think that would be the APM demo. Let me see if I find the chat again, and then I can hopefully answer some questions. There's one more question from Riza. Is it better to search by terms or to search by filter? That's a rather easy one to answer. If you only want to include or exclude documents because you say, I want to search for region EMEA or I want to search for region Africa or things like that, then always use a filter. because you don't execute, you don't do any scoring then. A filter means don't score. The score is not computed. And if you do a must part in a Boolean query, for example, you always calculate the score. And if you don't need that, then don't do it. Like, let's see the way you can basically figure out, do I need to search for something or do I need to filter something? If you don't want to compute a score, always filter.
Okay, we don't have any other question. So thank you, Alex, for your time, for the good presentation. And thank you, everybody, for being with us online. And see you soon. Thank you.